Hi, this is Sean Chua from simplecemconcepts.com. Welcome back. Now, today we're going to discuss a very important topic in chemistry. This is known as rate of reaction. Now, all chemists and chemistry students should know this topic very well because different chemical reactions will proceed in different rate. The common chemical reactions we can think of, which also means that will be tested on in examinations, will be acid reactions as well as reactions such as halogen or metals displacement reactions. Now, let's take a look on the meaning of rate. Rate in simple math, alright, is known as the change in something over the change in time. This is the most easiest way to look at rate. So in the chemistry lab, what we can do is to observe and track the change in certain properties of a chemical reactions versus the change in time using a stopwatch or a stop clock. Now let's use an example to discuss further. Let's say it is an acid metal reaction. So magnesium ribbon reacting with hydrochloric acid, that will get you a salt, magnesium chloride solution, as well as your hydrogen gas. So using this reaction, there will be two simple ways that you can measure the rate of this reaction in the school laboratory. What I can do is, in the first way, we can measure the volume of gas produced. In this case, is volume of hydrogen gas. We can set up this apparatus. We use a gas syringe. Alright, so I'm going to draw a simple diagram to show you. We're going to use a gas syringe, and then we're going to pass it, a gas syringe, so it's graduated, and you can read it off from there. We're going to put it inside a conical flask with a rubber bung. Alright, so let's say it looks something like this. So you have your acid, HCl, and then let's say you have some magnesium, alright, ribbon over there. So as reaction progress, bubbles, which is hydrogen gas, the gas itself, the product, will be released from the solution, and then it will go all the way up in the gas syringe. So you can collect, right? You can collect the volume of hydrogen gas itself, and this will be a cumulative result. So you have time and you have volume of H2 gas. So you can track them. Okay. Now the second way you can measure them is to measure the mass of the reaction vessel or the reaction mixture. So I'll write this mass of reaction mixture. Alright, mass of reaction mixture. So what we can do over here is we're going to use a flask, a conical flask. Again, let's say we have your HCl here, and you put in your magnesium solid. Alright, you're going to use a mass balance, so XXX gram, and this is your mass balance. We're going to put some cotton wool here. Now the cotton wool is to prevent acid spray because the reaction between a metal, magnesium, and your hydrochloric acid is quite vigorous. So the reaction will produce gases, and some of the acid might spill out, might splash out. So it's to prevent acid spray, the technical term that we like to use. Now, so in this way, what we measure, once again, is the mass. This is time, and this is mass of the reaction vessel. Alright, so we can track it using a stopwatch or a stop clock, and you'll see a certain trend in the results. In terms of volume, if you measure this, you realize as time progresses, cumulatively the value will increase because more and more gas will be collected at the gas syringe. Now, if you measure the mass of reaction mixture, if you look at it, initially you have metal and acid in. First, second, third second, as reaction progress, hydrogen gas and salt solution will produce. The solution, the salt solution, will still be inside the container, the flask, but hydrogen gas will have escaped into the surrounding. And because of that, we'll expect, right, the value to decrease. So using the values over there, we will then be able to look at the rate of reaction. Now, normally in this topic, we'll link it back to a concept called rate graphs. So let me show you the respective rate graphs and how it look like. So in this case, alright, let's make this longer. The rate graph over here will be drawn as this volume of hydrogen gas. So the rate graph looks something like this, and then you tend to have this. A typical rate graph will look like this, where it starts to plateau, become a horizontal line with gradient 0. It's clear at this point. Whereas if I measure the mass of reaction vessel, the rate graph will look like this. So this mass of reaction mixture. Alright, so this is in gram, whereas this is in cm cube. Okay, so let's see how it look like. Alright, this is 0.0, this is time. Let me put in all the important information. Now, so over here, mass of reaction vessel. At the start, there's a certain mass. As reaction progresses, hydrogen goes to the surrounding. Alright, the mass will decrease. Do note that you're going to hit a plateau where the line becomes horizontal, gradient 0 once again, and then the line will never reach 0 gram. This is because there's still the salt solution in terms of magnesium chloride, okay, as well as possibly some of the limiting reactant that's not, so the excess reactant that's not used, they will all be in the flask. So it will never hit 0. Now, these two are known as rate graphs. Now, to describe rate graphs, there are 3 sections. Alright, a usual rate graph. Let me show you, and both graphs will show you the 3 sections accordingly. The first one is at the start. Let me call this point 1, and then after a while, this is called point 2. When it starts to plateau, we call this point number 3 or section number 3. Similarly, over here, this is point 1, and then after a while, point 2, and here when it starts to become flat, become plateau, is point 3. Now, what is the difference between point 1, point 2, and point 3? You'll be asked to describe the shape of the rate graph. So it's important that you have some of the keywords with you. Now, at point number 1, whether it's here or here, you realize what? You realize for the shape, alright, of the graphs, this is the steepest. So at the start, alright, I'll just use bullet points here. At the start, the gradient is steepest. Gradient is steepest. Alright, why is the gradient the steepest? The reason is because the reaction is fastest over here. Alright, it's quite obvious. Now, and then at point number 2, section 2, what happened is, this is after a while, you realize the gradient, the gradient is very steep here, it becomes gentler. So gradient becomes gentler. Gradient gentler, right? Oops. Becomes gentler. And why is the gradient gentler? Because the reaction is slowing down. So we're going to have all this description. You were asked to explain. And then once it hit this point where it starts to plateau, alright, what happened is this is at the end of reaction. And you realize that the volume of hydrogen gas does not change anymore over here. And the mass of reaction mixture also won't change after this point. So this is known as at the end of reaction. What happened is the reaction has stopped. So reaction stopped. Why has the reaction stopped, you ask? It's because the reactant has been used up. Normally we will say the limiting reactant is used up. Alright, it's used up. Now, so this is the description and the explanation for your rate graphs. And once again, rate of reaction is a very important topic in chemistry. You need to really master this topic in order to do well for your chemistry. I hope you enjoyed the video today and learned a great deal about rate of reaction. Feel free to share our videos with your friends, and I look forward to seeing you in the next video. Thank you.